Good morning, everybody. Today we're going to be finishing out our notes packet on momentum, impulse, and conservation of momentum. We're picking up right here at the last page where it says non-collisional events. Now, last time we looked at collisions, objects interacting in a system where they bang into each other, they collide. And momentum is conserved always during any type of collision. But there are other types of interactions where momentum is conserved within a system of objects that are not actually collisions. For example, a pitcher who throws a baseball towards the batter, a rider unseated from his horse, an escape pod separating from a spaceship. These are all examples of non-collisional events. That is, the objects start out together and then they separate, which is sort of a reverse process from a collision. In fact, you might hear some physicists call them explosions. I do not like, however, to use the word explosion because obviously if you have a rider unseated from his horse, neither one of them exploded. They just call it that because the pieces are separating from each other. Okay, so let's look at what this is about. Now, in a non-collisional event, momentum is still conserved, just like with collisions, as long as the system stays isolated. Again, just like collisions. Look at this example. If you have a 50-kilogram astronaut, let's call that the mass of the astronaut, and he's on a spacewalk in outer space holding a 10-kilogram mass, and I'm using M sub M for the mass of the mass. They are floating in a stationary position when the astronaut throws the mass away from himself. He gives the mass a speed of 15 meters per second. So when it leaves his hand, that mass will be moving forward at 15 meters per second. So let us consider the event. The event is the throwing. So you have before he throws and you have after he throws. Well, before he throws, the mass that he's holding isn't moving. Remember, they're stationary. But after he throws, the mass is moving at 15 meters per second. So that would be the final velocity of the mass. Now, you have to remember when such an action takes place, Newton's third law does come into play. If he exerts a forward force on the mass to accelerate it forward, then according to Newton's third law, the mass must exert an equal and oppositely directed force back on him. Now, since this happens in a time period, the force each one exerts being equal and the time being the same, that means the impulse imparted to each is also the same, just in opposite directions. So the mass will move in one direction at one speed. So guess what the astronaut does? He moves in the other direction at some speed. Now, is it the same speed? No, because their masses are very different. So let's take a look. If we consider the astronaut to be and the mass to be the system, then the initial momentum of the system would have to be zero, since both masses, the astronaut and the object, are at rest to start with. Now, what should be the final momentum of the system? Well, this is a non-collisional event. Momentum must be conserved as long as our system, the astronaut and the mass, are isolated from other outside influences. So, if the initial momentum of both are zero, then the total final momentum of both must also be zero because momentum must be conserved. Now you're thinking, well, Miss Pepitone, if they're both moving afterward, how can the net momentum, the sum of the final momenta, be zero? Easy. We have to remember that momentum is a vector. So the mass has a momentum in one direction and the astronaut has a momentum in the other. They must be equal as well as oppositely directed. So they will add to zero to give a final total momentum of zero. All right? And I believe that's what I say right here. Since the mass is moving in one direction, the astronaut is also moving and they both have momentum. But to add to zero, the two momenta must be equal and oppositely directed. So the final momentum of the astronaut would be equal but oppositely directed to the final momentum of the mass that he threw. If we look, we can determine the final momentum of the mass. We know the mass is 10 kilograms and it's moving at 15 meters per second. So the mass itself in the positive direction has a momentum of magnitude 150 newton seconds. So what would be the magnitude of the man's final momentum? Well, it should also be 150 newton seconds, but in the other direction. So now knowing the man's final momentum and his mass, we can determine his final speed. So set the mass of the astronaut times his final speed equal to the final momentum that he has, and you get -3 meters per second in the opposite direction from the mass. So notice the mass, being the smaller of the two objects, must have a larger final velocity so that its momentum is the same as the mass of the astronaut, which is much bigger, and his smaller final velocity. All right, and basically that's the end of it. Now, I do have some videos that I have added into this folder, I believe, that will help you understand this a little bit more. Today, we're just filling in these notes, okay? And tomorrow, you are going to do, I believe, a discussion with a video. And we'll also be working on some other things this week dealing with non-collisional events. So make sure you do each folder each day, keep on top of it, and you won't get behind. They won't take that long. I told you we would be slowing down, so I've made sure that these don't take terribly long. Okay, thanks very much. Bye.